All right, welcome back, Atlas. This is part 2 of our problem-solving series of statics and mechanics of materials based on an aerospace engineering course. And this essential topic number 2 is going to be covering moments. And again, we're going to ask the question, what problems do I need to know how to solve in order to master this topic? So, things you need to know. You need to know how to apply Newton's second law to solve for reactionary forces. You need to determine which forces participate in any given moment calculation. We're going to need to utilize the directional unit vector. I have it here as lambda mn. It could be any two sub-letters. And we're going to use that to calculate moments about any point. Okay, and then we're going to ultimately have to know how to compute a cross product. Okay, so that's I cross F, or X cross Y, Y cross Z, Z cross X, or any other combination thereof. And I have this handy dandy little diagram here where if we cross X cross Y anywhere in the red direction, we'll be remaining positive. But if we calculate a Y cross X, X cross Z, or Z cross Y going in the opposite direction, that'll be following the blue arrows, that'll be adding a negative to our cross product. Okay, so covering what we need to get into, let's go ahead and get into the problems. So first up, we're going to calculate reactions using Newton's second law. Okay, give you a broad overview of what we're going to be doing next. Next video is going to be calculating the moment about a point using this diagram. And last but not least, we're going to be utilizing lambda to solve for a moment about an axis. A little more complex. Going to be bolstering on a couple skills we've used in the past. But let's get into calculating reactions using Newton's second law. Problem statement reads, given F is equal to 25 kilonewtons, M is equal to 15 kilonewtons meter, and L is equal to 6 meters, find the reactions at point A. Okay, so observing our diagram, we see point A is rigidly attached to a wall. So we should get all three reactions in 2 dimensions. Get an X, get a Y, get a moment. We have a concentrated moment labeled M here, and a concentrated load labeled F. Okay, it looks like it's acting at a distance of half the length of the beam, and there's nothing going on out at B. It's just hanging in free air. You can think of this as a post to hang a sign outside of a business, something like that. Okay, so now that we understand the diagram, let's go ahead and jump into our top down. See that I have things laid out ready here. I have my simple diagram. I have all my known tables that designate what these variables mean and their units. I have my want table here, and based on the problem statement, I'm going to go ahead and come back to that. So we're going to go ahead and jump into step number 1 in solving this problem. I have a couple people in my class that always want to tell me what step 1 is, and that's always going to be get a pen that works. Draw free body diagram of AB. Okay, because remember, this is not a free body diagram. This is a depiction, a simplification of what's going on. We want to draw a free body diagram. So that means we have 3 different parts. We have the actual body itself. We're going to label that A and B. We have a concentrated load here, labeled F. We have a concentrated moment, labeled M. Okay, and then I have a couple of distances here to copy down. Okay, so here we go. All right, so I have copied down all the information that I needed, but you'll see that I have removed the wall at point A, and it looks like I didn't copy down A and B. Pulled that in there. So at A, we've removed the wall. B has nothing, it's floating out in midair, so that's fine. We need to replace the wall with a couple reaction forces that happen at A. And because A is rigidly attached to the wall, we're going to get 3 forces there. We're going to get a AX, we're going to get an AY, And we're also going to get a moment. We're going to call this moment about A. Okay, and I draw MA this way because I'm using a regular right-hand coordinate system. So I draw this little picture because this is X, this is Y. And if I... Ooh, eye itches. If I recall your attention to that little diagram I have, X cross Y is going to equal Z. X cross Y is going to equal Z. So that's the good old right-hand rule there. So point in the direction of X, this is the direction of Y, and if you curl this finger, the Z direction is your thumb, and so it curls that direction. So we know that's positive. Okay, so we have all of our reaction forces done or drawn in. We have our concentrated moment copied down, and we have our concentrated load copied down. Free body diagram is done, so we can go ahead and move on to step number 2. And so step number 2, I'm going to be applying Newton's second law. N2L is what I use for Newton's second law. Okay, let's go ahead and do the low-hanging fruit. The summation of the forces about the x-axis, or in the x direction, is going to be equal to AX. That's a force in the x direction. MA, M, AY, F, there's nothing else that participates in the force in the x direction, so that's going to equal 0. And, oh geez, now we can go ahead and fill in our want table, because the problem statement wanted the reactions at point A. AX was a result of me removing the wall. So the wall is reacting to the forces on the beam, and so AX is going to equal 0 kilonewtons. And while I'm here, I'm going to go ahead and need AY equal to something in kilonewtons, the units of the day here. And we also have the moment about point A, and that's going to be something in kilonewtons meter. Okay, just like this M. Okay, so AX equal to 0, so we can go ahead and box that answer, report it up there. And so now let's go on to the forces in the Y direction. Okay, now we're going to have AY participating. That's in the positive Y direction. Let's go ahead and make this clear to my reader that we're going to be using this as the X axis and this as my Y axis. So the origin is at point A. Reasonable. So AY is pointing in the positive Y direction, so it remains positive. F is pointing in the negative Y direction, so we're going to bring that in as negative F. And nothing else participating, nothing else is vertical in this, so we'll set this equal to 0. Okay, we know F here. We don't know AY, so we'll rearrange this to solve for F. AY, F is negative, it's going to go to the right-hand side, become positive. AY is equal to F. And then we'll substitute AY equal to 25 kilonewtons. Okay, another answer. Report that up there in our want box. And now our only task left is going after the moments about point A. MA there, because we know M, we know F, we know AX and AY. So we're ready to go. So we'll take the summation of the moments. Okay, big key with moments is you can take the moments about any point, and they should all equal out. You should not have differing answers based on where you take the moment about. Okay, so when I take the moment about any point, this is going to be equal the summation of R cross F's. Okay, that's where this X, Y, and Z business comes from, X and Y here. So I need to have an R vector, I need to have an F vector. Okay, and if you don't know what R cross F is, I have this little piece of paper here. An R vector is a distance. In green, because I have my L and my L over 2s in green, and then I have a force vector that is perpendicular to the moment arm, F, drawn in red, AX, AY, all the forces are drawn in red, so that's why this guy is red, must be perpendicular. Okay, so we'll come back to that in just a moment. And if I want to take the summation of R cross F's to get MA, I want to be able to knock out as many forces as possible so that my equation doesn't get too long. Okay, because I can pick A, I can pick the midpoint, I can pick B, I can pick somewhere over here, call it C, and say that it's X distance away from A or B. Okay, some of these are smarter than others. Okay, and I say that because if I pick a point, say point A, and if I look at AX, AX does not participate in the moment calculation because its moment arm, its R value, is 0. We only have this. We don't have a moment arm, so it doesn't participate in the moment calculation. Its R value is equal to 0. Same thing with AY. AY passes through the point A, which means it has a 0 moment arm. No part of AY acts perpendicularly at a distance away from A, so it doesn't participate either. So if I pick point A, I'll have MA, M, and F that participate in this moment calculation. Another good option would be the midpoint. Okay, and if I choose the midpoint, F does not participate. AX does not participate. By reasons of the principle of transmissibility, if I move AX along its line of action, it also has a 0 moment arm and does not participate, but AY does. So AY, MA, and M will participate. Still 3 terms in that equation. Just a little more cumbersome. I would not prefer it. So I'm going to go ahead and go with some of the moments about point A and just use our origin as what I want, or as my calculation point. So I'll do the summation of the moments about point A equals the summation of R cross F's. And we'll move on to filling in the moment about A. So the first R cross F, we'll go ahead and do this F vector here because that is actually an R cross F. M and MA are both moments, concentrated moments, that will participate in this moment calculation even though they are not R cross F's. Okay. I guess I should put plus moments in this. So the summation of R cross F plus the moments all go into summation of the moment about A. So summation of moment about A in the F, and we're going to use this cross product style, and then I'll show you a different way using this little guy. I think it's super easy to use this. All right, so if I want to use the regular cross product using X, Y, and Z, I'm going to say that from A to F is a distance of L over 2. Okay, so this term is going to get an open parentheses, and I'm going to get an L over 2, which is 6 divided by 2, 3 meters away in the X direction. Okay, so 3 meters X, that's the first R value, and then we're going to cross that with the F vector. And that is traveling in a downward motion, which opposes our positive Y convention. So we'll get negative F Y hat there. Okay, that is our first term. This is the R vector. This is our X vector. So first term done. We don't have any other concentrated forces to deal with because again, AX and AY do not participate in this moment calculation. So only the concentrated moment given M will participate and MA will participate. Okay, so we can start with MA. MA is drawn counterclockwise, which agrees with our positive convention here. So we'll call that MA. And then we are going to subtract M because M is traveling clockwise, which disagrees with our positive convention. Picture here of minus M. Okay, again, AX and AY don't participate, so we'll set this equal to 0. And let's go ahead and carry out this cross product, and then we'll go ahead and solve for MA, because that's what we're ultimately looking for. M is known, it was given. So let's carry out this cross product. So first things first, we're going to have 3 times negative F right here. So we have negative 3 times F is 25 kilonewtons. Okay, now we have an X cross Y. So if I have X cross Y, I'm going in the positive direction. This term does not get an extra negative, and so it can remain the way it is. Okay, and if I cross X with Y, I get a Z. That pops out. Okay, and then we'll add MA, and MA acts around the Z axis. I know you can't see it, but if my index finger is the X and my middle finger is Y, Z comes out of the page right here. That's the out of the page there. So this will also get a Z hat and minus an M Z hat. Probably should have inserted. Let's go ahead and put in a value for M since we know it. M is 15 kilonewton meters. And I'll put that over here. Kilonewton meters equal to 0. Okay, so now we have all of our numbers in here, and we're solving for MA. So MA is positive, so it's going to stay on the left-hand side. So we'll write that down first. So I'm dropping off the summation of MAs, and I'm simply solving the right-hand side of these equations. So MA, I'm going to drop off the Z's because all these terms are going in the same direction about the Z axis. So I'll go ahead and drop that off. And so MA is positive. This term is negative. So when it goes to the right-hand side, it'll become positive. And 3 times 25, 75 kilonewton meters. Okay, negative 15 goes to the right hand side, becomes positive. Okay, so MA is going to be equaling 90 kilonewton meters. Okay, let's do a vibe check. Does this make sense to us? Remember, AMA is the reactionary force of the building on the beam that's sticking out of their front door. Okay, so if I have this beam and I sign up and I hang a sign there, I'm going to be having a concentrated load at F. Okay, if it wants to push downward this direction, I'm going to have something from the building that wants to push it the other direction. Right, because we're in equilibrium, nothing's moving, nothing's accelerating. So as this sign pushes down, the building has to return something to rotate this upward. So does make sense that MA is in the positive direction. And it should be at 90 kilonewtons meters. Okay, box that. And that's all she wrote. We've now found all of the reactions at A for this diagram. That's all I got for you today. If you'd like this, if it's helped you in any way, shape, or form, give me a like, thumbs up, leave a comment, ask any questions, and consider subscribing. I'll be doing this. Anyways, Atlas, I love you. Can't wait to meet you, and I'll see you next time. Bye-bye.